Welcome back. Today we are doing 5.1 quadratic transformations, part 2, and we're going to be doing graphing today. As you can tell, I already have part of my grid up here for number 1. F of x equals x squared minus 4. Now, for today's lesson, I do have a variety of colors to help us visually see our transformations. If you don't have any colors, that's okay. It is helpful though. First thing we're going to do on our graphs is start with the parent function. Now remember, the parent function is the most basic of the quadratic functions, y equals x squared. Now remember, from our previous lesson, we had graphed this before. So we started with a vertex of 0, 0, and then we found points 1, 1, negative 1, 1, 2, 4, negative 2, 4, and then let's go one more for today's purposes. If I were to go out to x equals 3, well, 3 squared is 9. So 3 go up to here. And therefore, my reflective or symmetric point would be negative 3, 9. And so this is my parent function. Now, to look at the transformation being made on this graph, we have to think back to our lesson yesterday. So to know, what does the minus 4 mean in reference to my graph? Well, in reference to my graph, this means we have a vertical translation down 4 units. So how will that look? That means every single point is going to go down 4 units from my parent function. So my vertex at 0, 0 is going to go down 4 points. 1, 2, 3, 4. That means my new point is at 0, negative 4. I'm going to do the same thing for each of my points. Down 4. 1, 2, 3, 4. Down 1, 2, 3, 4. And down 4. 1, 2, 3, 4. And then I'm going to connect those points. So we can see that the entire graph has shifted from the parent function down 4 units. Now, before we go to the next one, let's talk about a few things. So first thing we're going to talk about is our domain and range. Now remember, our domain are your x values. What does my domain equal? So if we're thinking about possible domain or possible range values, we want to think what number is restricting the graph. So if we're thinking about our x values, is there ever going to be an x value that I can't use? Could I substitute in 10 for x? Could I do 12, 100, 10 million, negative 10 million? No, that means any number I could graph if I really wanted to keep graphing on my x values forever. So therefore, that means that my domain is all real numbers. And we have our all real number symbol. Then we have our range, which is our y's. Now remember, if you're identifying domain and range, you have to at least put a D or an R, or you can write out domain and range. Now for my range, it's going to look a little bit different because, as you can tell, we do have a certain restriction on my y values. My graph doesn't end up actually going past negative 4, right? I'm never going to have a value lower than negative 4 on the y's because my graph is going up. So because of that, that means I have a restriction. So we first start with our y value, which is f of x for this problem. And then we have our colon, which remember that means such that in math. So we have f of x such that f of x is what? What's our restriction? Y value or f of x must be what? Well, it must be greater than -4, and more specifically, greater than or equal to -4. So that is our domain and our range. All our f of x or y values are going to be greater than -4, greater than or equal. Okay, last but not least, we have our axis of symmetry, which you can shorthand as AOS. Remember, that is the line of symmetry going through the vertex of your graph. So therefore, that line would be x equals 0. Okay, even though x equals 0 is the original one for the parent function, this graph only moved up and down. So therefore, the vertex is still on that same line of symmetry or axis of symmetry. So therefore, our axis of symmetry is still x equals 0. Okay, great job. Let's move on to number 2. Okay, let's try number 2. Number 2, g of x equals the quantity of x minus 4 quantity squared. So again, we're going to start with that parent function. And remember that parent function will never change. So your graph will always be the same for that parent function, regardless of the new problem that you're working on. Okay, here's our parent function. Now let's talk about the transformations that are occurring on this graph. Now, in the last graph, we also had -4, but this one is inside the quantity with x. And so that means that this one is a horizontal translation. And remember, because the original equation is minus, that means this is actually to the right 4 units. Now, what's that going to mean for my vertex? Now, remember, your vertex in vertex form is HK. Your H being your value here. Now remember, because the original equation is minus, when you pull that number out, it's actually the opposite of what your brain thinks. And so your vertex x value is going to be 4. Now, my k value would be anything on the outside, added or subtracted. And since I don't have anything, that means I'm adding 0. So my vertex is 4, 0, which makes sense because my parent function is 0, 0. So if I'm moving to the right 4 units, that means my x value would move to the 4. So let's see what happens when we move our graph to the right 4 units. We'll move everything 4 units over. So we have 1, 2, 3, 4. One, two, three, 4. 1, 2, 3, 4. Now, it is important that you know that I already had those axes drawn in, but it is pretty clear what's going to happen in your graph, especially when you have the basic ones, like such. If we know what the transformation is, we know what's going to happen on my grid. So because I know there's a horizontal shift, I know that my x-axis is going to have to be larger on one side or the other, depending on which direction I'm going. Similar to number 1, because I knew I was going up or down, I knew my graph would have to be moving up and down. So therefore I made my grid accessible to do so. Now, it is important to make sure you have a little bit of space just in case you need more space than you think. So always make sure that you don't make your graphs right on top of each other. There's a little wiggle room. Okay, now let's talk about the domain and range for this graph. So we have our domain. Now, again, is there going to be any restriction on my x values? Is there any x value that I would ever not be able to graph? The answer is no. So therefore, that means my domain is all real numbers again. Now for my range, is there a restriction? Yes, because restriction for range would be up and down. And I don't have any negative y values. So therefore, all my values are greater than or equal to 0. So my range would look as such. So we do our y value, which is g of x in this problem, such that g of x is greater than or equal to 0. And last but not least, our axis of symmetry. Now, our axis of symmetry is going to be different now because my vertex has changed. Where is going to be that vertical line or axis of symmetry to reflect or symmetrical of my graph? Hopefully you said x equals 4, because remember, it has to go through the vertex, and so therefore it should equal the x value of your vertex. So x equals 4. And it is an equation, so the x equals is important. Great. Let's go ahead and move on to number 3. Okay, let's try number 3. Number 3 is y equals the quantity of x minus 2 quantity squared plus 3. So we're going to start with our parent function. You're going to get very, very good at making that parent function. Okay, so now let's talk about transformations. So it is very important at this rate when you're graphing that you do your transformations in a certain order. When we talked about them from the equation, it really didn't matter how we listed them on that assignment. But now that we're in the graphing, we do have to graph our transformations in a specific order, and that order being PEMDAS, meaning we start with the parentheses and move our way out. So because we start with our parentheses, that means our horizontal translation will always be our first shift on our graph. So our first transformation is going to be a horizontal translation right 2 units. Then we would move on to what's outside the parentheses, which is our exponent. But for the purpose of this lesson, we're doing just quadratics. So it's always going to be squared. And then you would multiply by something on the outside, right? We normally have a out there. But a is only 1, so I don't have to worry about the a this time. And then last but not least will be my k value, adding and subtracting at the end. So therefore, my second transformation is a vertical translation up 3 units. Now, because we're going to be doing more than one transformation, we're actually going to do dotted lines from here on out to represent our transformation. So the first thing we have to do is a horizontal translation right 2 units. So I'm going to move all my points to the right 2 units. Okay. Now, rather than connecting this with a solid line, I'm going to do a dashed or dotted line because this will not be my final image because I have more than one transformation to complete. And I should have picked pens that didn't bleed. Then we need to do our vertical translation up 3 units. So now I'm going to take each of my points and move it up 3 points. Lost track where I was, sorry. And now, because that is my last transformation, I will now make this one a solid line. Okay. On the next example, we will start making the parent function in a dashed line as well so that we can clearly indicate that the solid line is our last one. Okay, let's talk about that information a little bit. So on the last example, we talked about the vertex. Now, what would the vertex be on this problem? Well, it looks like it's at 2, 3. And remember, the vertex comes from these points. Remember, vertex x value is your horizontal translation, and your k value is your vertical translation. Okay, let's look at that domain and range. Okay, domain, any restrictions on the x value? Sure not. There's any x value I want to substitute or find or move, I can do so. Therefore, domain is all real numbers. Now let's look at range. Okay. So range, we set it up with our y value, which is y this time. Now, what is our restriction on y? So looking at our final answer, which is the pink answer, we don't have any values that are less than positive 3. So that means that y must be greater than or equal to 3. And last but not least, our axis of symmetry. Now remember, your axis of symmetry stems from your vertex. So it has to go through that vertex. So therefore, x equals 2. Now, before we move on from this one, does anyone see any patterns with what we have on our domain, range, and axis of symmetry with our transformation and vertex? Hopefully you notice that your axis of symmetry, which we've talked about before, this number stems from your vertex x value. So whatever your x value of your vertex is, that's the same x value for your axis of symmetry. And now something you may not have noticed, or something that would be newly noticed from this lesson, is that your range restriction is going to be based on the y value of your vertex, because that point will indicate if you are going above or below that point. So therefore, the 3 comes from our vertex. So those 2 tips will help you in the future with your range and axis of symmetry. Okay, we're going to go ahead and move on to number 4. Okay, number 4. F of x equals negative x squared plus 2. Okay, now again, we want to make sure we're doing our transformations in order. So our first transformation, we don't have anything connected to x within the parentheses, then we would have what we have multiplied. Now, we're just multiplying by -1, so therefore we are going to have our reflection over the x-axis as our first transformation. Then our second transformation will be our vertical translation up 2 units. Now remember on the last question, I said that we're going to start doing the parent function as a dotted line so that the solid line will be our last final answer so we can really see the transformations happening. Now, this will also be required on your homework that you show different transformations in each step. It doesn't require that they're colors, but if they are colors, I would suggest keeping them the same colors throughout your assignment. So for example, I have my colors set so that I don't forget which color is which so that it's consistent throughout my assignment. So, work through the notes. So we start with a parent function. And we're going to do a dashed line. Now, do the best you can. The whole purpose of the dashed line is just simply so that we can tell the difference between transformations and the final answer, starting with our parent function. So now we're going to do our reflection over the x-axis, which is green. So when we reflect over the x-axis, that means everything that's here is going to go upside down. Okay? Essentially, if the graph looks like this, we're going to now make it look like such. Okay, it's going to reflect over the x-axis. So the point 0, 0 is going to stay, because obviously when you reflect 0, 0 over, it stays there. But this one, when reflecting over, it will now become 1, negative 1. And this one will become negative 1, negative 1. Okay, same thing, reflect over. So when we're reflecting over, keep in mind, it's going to be the same distance from that x-axis, or sorry, yeah, from the x-axis. So since this is 1 away, now this is 1 away. This is 4 away, so this is going to be 4 away. So now we have a reflection. Okay, I'm going to dash my line. Because that's not my last reflection. Oh, see, I told you. That bleeding pen is not going to be my friend today. And just to keep my color straight, I'm going to go back here and circle this so you can see what I've done previously. So you can really make sure you remember. Okay, now we need to do our vertical translation, which for me is 2. So everything is going to go up 2 units. So from here, we're going to go up 2. Since this is my last transformation, this one is going to be a solid line. And if you're using colors, feel free to go slowly, just because I know that once you make a mistake, unless you have those fancy erasable ones, you can't change it. Now, I do know some students that will flip their graph upside down to draw it because it is a little bit harder to draw and connect when it's upside down. For some reason, for me, I just have to think a little bit more just to make sure, because that natural up position just is a little bit more natural. Okay, let's go ahead and talk about our points. So thinking about our vertex is 0, 2. Now remember where those connections are. So first we have is our domain, which there's no restriction still, so all round numbers. Our range, there is definitely there's definitely a restriction, but it's a little bit different than before because our graph is upside down. all our points are smaller than 2 versus greater. So therefore my range would be f of x such that f of x is less than or equal to 2. Because it's upside down, because we have a reflection, all my points are going into the negative values versus where we're normally going up to the positive values. So now we have less than or equal to 2. And remember that 2 comes from that vertex. And last but not least, our axis of symmetry is x equals 0. However much it moved, it did not actually move from that same vertical position. So therefore x equals 0 is still my axis of symmetry. Okay, great job. Let's move on to number 5. Let's look at number 5. So number 5 is y equals 1/2 x squared. So thinking about our transformation, the only thing that's affecting our normal y equals x squared is this half. So remember, a half is going to be our compression. Specifically, it's going to be a vertical compression. By a factor of 1/2. So let's start with that parent function. Again, remember that parent function never changes. It will always be the same points. Sorry, mine got a little weird there. Okay, now this is our first compression, well, or stretch really. And so we are going to be working with orange. Now, to compress something by a half means that everything that you have is going to get smaller, right? It's going to be half the size. So if we think about our points, for example, our original point I'm going to move my paper here for a sec. So our original point, we have 0, 0. If I compress this by a half, when I'm thinking about compressing it, am I going to be changing what I input to the equation? No, I still have to have 0 as my starting point. So your y value is what's going to change, also because it's the vertical compression, and y is your vertical values. But when I compress 0 by half, it's still 0, 0, right? Nothing's changed. Let's think about our 1 value, our next value, which is normally 1, 1. So if I compress my value, being my vertical value, well, 1 times a half, or compressed by a half, would now be 1, 1/2. Okay, how about 2? 2 is at 2, 4. So 2, 4, our y value will be compressed by a half, will now be 2, 2. And then last but not least, our 3, 9 will be compressed, and will now be 3 and 9/2. So what does that look like on my graph? We have 0, 0. We have 1, 1/2. And my reflective point, symmetric point. We have 2, 2. And we have 3 and 9/2, which 3 and 9/2 is going to be 4.5. Okay, and we're just going to do one more point. And let's see what happens at 4. Well, my normal point would be 416, which I would know from just 4 squared is 16. So therefore that point would now be 4, 8. Now doing this extra point kind of really helps visualize what's happening here with my graph. Ugh, sorry, I gotta do better at this, sorry. Okay, my original graph was a skinny U, and now it's like a little bit of a wider U. So what happens when we compress things, it flattened things. So we had a U that was like this, and now it's a little bit wider. So it's kind of like it smushed it, kind of compressed it, it flattened it. There's lots of different words to describe it. But as you can tell, again, because it compressed by half, all those values are now flattened or compressed. So therefore our graph is just a little bit wider. Right? And let's talk about domain, range, and axis of symmetry. So our domain, still no restriction. So we have all real numbers. Our range, y such that, well, it actually didn't go anywhere from 0, 0, so y is greater than or equal to 0. And our axis of symmetry still didn't change either. So therefore, axis of symmetry is x equals 0. Oh, and we didn't talk about the vertex. The vertex stayed the same. Vertex is 0, 0. Okay, great job on number 5. I'll see you in the next one.